Acids, bases, and salts are chemical compounds that affect your life on a daily basis. Familiar examples of acids, bases, and salts are battery acid, laundry bleach, and table salt. Commercially, acids and bases are required in the manufacture of thousands of commonly used products. For example, sulfuric acid is required to produce, among other things, fertilizers, explosives, steel, and plastics. Acid-base balance within living organisms is essential for life's processes. Although the acidity of our blood is constantly fluctuating, acid-base balance is maintained within a narrow margin. A significant shift in this balance quickly results in death. Most acid-base chemistry involves the transfer of protons from one compound to another. Acids are compounds that donate protons. Bases are proton acceptors. Acids and bases react with one another to form compounds known as salts. In this program, you will review atomic structure, chemical compounds, and chemical equations, and apply these concepts towards an understanding of the properties of acids, bases, and salts. This program will also explore the chemistry of water and explain the concept of pH. You may already be familiar with some well-known characteristics of acids and bases. Certainly you wouldn't want to handle battery acid with your bare hands. Nor would you want to use certain household cleaners without gloves and proper ventilation. Battery acid is a solution of sulfuric acid, and many products, such as drain openers, are strong bases. Acids and bases can burn your skin and must be handled with caution. Remember, if you ever spill an acid or base in the laboratory, immediately alert your instructor for advice on how to clean it up safely. Certainly, not all acids and bases need to be avoided. Many popular food items, such as soft drinks and pickles, are acidic. Citric acid is responsible for the tart or sour taste of citrus fruits, such as lemons, oranges, and grapefruits. Acetic acid is responsible for the sour taste of vinegar. Bases, which are sometimes referred to as alkaline substances, or simply alkalis, are found in antacid tablets, baking soda, and soaps. Perhaps one of the first things you learned in chemistry is that an element is a chemical substance that cannot be separated into simpler substances. Elements such as gold and carbon are the building blocks of matter. When two or more elements combine, they form compounds. Water is a compound that is composed of the elements hydrogen and oxygen. Acids, bases, and salts are compounds that ionize in water. Ions are atoms or groups of atoms that carry an electrical charge. Cations are ions that have a positive charge, and anions are ions that have a negative charge. When acids, bases, and salts dissociate, they separate into cations and anions. Chemists use the terms physical properties and chemical properties to describe matter. Physical properties may include the structure of a compound, its formula weight, boiling point, or melting point. Chemical properties describe how a compound reacts with other substances. The physical and chemical properties of acids and bases can be used to identify them. A primitive method for identifying acids and bases is on the basis of taste. Acids, such as those found in lemon juice, taste sour, and alkalis, or bases, such as soap, taste bitter. However, you are strongly cautioned not to attempt this method of identification. To illustrate this warning, examine the three solutions on your screen. Can you tell which one is hydrochloric acid, which is sodium hydroxide, and which one is water? Of course you can't, because they all look the same. If you value your life, the taste test is no way to determine the identity of anything. The use of an indicator is a much more acceptable test to distinguish between acids and bases. An acid-base indicator is a substance that turns one color in an acidic solution and a different color in an alkaline solution. One of the most common and easy-to-use indicators is litmus paper. Litmus is a natural dye derived from lichens. Lichens are organisms found on exposed rocky areas and come in a variety of colors, depending on the acidity of their environment. A thin paper strip saturated with litmus is known as litmus paper. Litmus paper turns red in an acidic solution and blue in a basic solution. Water is a neutral substance, which means it is neither acidic nor basic. Litmus paper does not change color in neutral substances or solutions. Acids and bases differ in properties related to reactivity. Acidic solutions react vigorously with metals such as magnesium or zinc to form new compounds. For example, magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. Bases, on the other hand, do not react with most metals. Acids also react with many non-metal substances. Acids, bases, and salts are all examples of electrolytes. An electrolyte is a compound that dissolves in water, forming a solution that conducts an electrical current. When an electrolyte, such as sodium chloride, dissolves, the positive and negative ions separate and are free to move about within the solution. In a solution of an electrolyte, ions are responsible for the transport of electrical charge through the liquid. The concentration of electrolytes is responsible for the degree of electrical conduction. Now that you have learned several properties of acids and bases, let's review some differences between these compounds that can be used to identify them. First, you learned that acids taste sour, whereas bases are bitter tasting. Then, we discussed how litmus paper turns red in an acidic solution, blue in a basic solution, and undergoes no color change in neutral solutions. Next, you saw how acids react vigorously with metals, such as magnesium, but bases did not. Finally, you learned that acids, bases, and salts are all electrolytes, which means they conduct electricity through a solution in which they are dissolved. Next, you will learn how acids and bases are defined based on the ions that they donate to solution. The properties of acidic solutions are due to the hydrogen ion. Often the term proton is used in lieu of hydrogen ion. The terms hydrogen ion and proton indicate slightly different concepts, but are used interchangeably by most chemists. It is the hydrogen ion, or proton, that is responsible for the sour taste of vinegar and the color change to red exhibited by litmus paper. It is also the hydrogen ion in acidic solutions that reacts with various metals. To fully understand how the terms hydrogen ion and proton are derived and what they mean, you must first understand the atomic structure of the hydrogen atom. The hydrogen atom is different from all other atoms because the most abundant isotope of hydrogen does not have any neutrons. This means that, in general, a hydrogen atom is composed of one positively charged proton orbited by one negatively charged electron. Therefore, a hydrogen ion, which has lost its electron, is simply a proton. Most acid-base chemistry involves liquid solutions. In chemical terms, a solution is a homogeneous mixture of more than one substance in the same physical state. Now let's interpret that statement. The components in a homogeneous mixture are so well blended that they cannot readily be distinguished from each other. The air you breathe, a glass of powdered lemonade, and salt water are all examples of homogeneous mixtures. Obviously, you cannot see the various types of molecules that make up these mixtures, even though you might be aware of what they are. Acid-base solutions are most commonly liquids. In a solution, one substance is usually considered to be dissolved in the other. The substance that is dissolved is called the solute. The substance that does the dissolving is called the solvent. This program will emphasize aqueous solutions of acids and bases. In an aqueous solution, the solvent is water. An acid is a compound that donates a hydrogen ion, abbreviated H+, to solution. The release of hydrogen ions as an acid dissolves in water contributes to the acidity of the solution. A base is a substance that donates a hydroxide ion, written as OH- to an aqueous solution. The properties of an alkaline or basic solution are due to the hydroxide ion. In 1884, a Swedish scientist by the name of Svante Arrhenius pioneered the study of acids and bases on the molecular level. While working towards his PhD degree, Arrhenius studied electrical conduction through solutions. Arrhenius was puzzled as to why some solutions conducted electricity and others did not. He believed that some compounds, such as sodium chloride, split into ions when dissolved in water, while others, like sugar, did not. Arrhenius devised a theory stating these free ions were responsible for conducting the current. After concluding his work on electrical conduction, Arrhenius went on to apply his knowledge of ions and their properties to define and explain acid-base chemistry. When acids, bases, and salts ionize, they form ions in solution. Arrhenius could not see compounds ionize, but he could infer the ionization by measuring the resulting increase in electrical conductivity. These and other experiments led Arrhenius to propose the first accepted definition of acids and bases. Arrhenius defined an acid as a substance that ionizes in water to release positively charged hydrogen ions into solution. He defined a base as a substance that ionizes in water to release negatively charged hydroxide ions in solution. Suppose a microscope was developed that could enlarge a drop of water to such a magnitude that the individual molecules were visible. Would you see that a sample of pure water contains only molecules of H2O? The answer is no, because pure water always contains small quantities of two other chemical species: positively charged hydronium ions, represented by the formula H3O+, and negatively charged hydroxide ions, represented by the formula OH-. These ions exist because hydrogen ions spontaneously shift between water molecules. You may have thought that hydrogen ions simply exist in solution as independent charges. Actually, hydrogen ions almost never exist in a solution independently. Hydrogen ions and their positive charge are simply transferred from one water molecule to the next. Water molecules are capable of self-ionizing, meaning one water molecule can spontaneously transfer a hydrogen ion to an adjacent water molecule. This transfer of charge results in a positively charged hydronium ion and a negatively charged hydroxide ion. You can think of the self-ionizing of water as a neutral water molecule splitting apart, resulting in two ions. When compounds such as hydrochloric acid ionize in solution, protons are released. These compounds are known as acids. Most bases ionize in solution to release hydroxide ions. Hydroxide ions strongly attract protons. Therefore, bases are considered proton acceptors. In a sample of pure water, self-ionization produces an equal concentration of hydronium ions and hydroxide ions. The balanced chemical reaction of the self-ionization of water can be used to determine the equilibrium constant, Keq. The equilibrium expression for the self-ionization of water shows the concentration of ions as a mathematical relationship. The brackets around each of the reactants and products indicate that the concentration is measured in molarity, which will be briefly reviewed in the next scene. The concentration of water molecules is so much larger than the concentrations of the ions that it is not significantly affected by the changes in ion concentration. This means the concentration of water is essentially a constant. Therefore, it can be removed from the denominator of the equation by multiplying both sides of the equation by the square of the concentration of water. The product of two constants, in this case the equilibrium constant and the concentration of water, is also a constant. This constant is called the ion product constant for water and is abbreviated as Kw. The significance of the ion product constant will be explained in the next few scenes. The amount of solute dissolved in 1 liter of water determines the concentration of an aqueous solution. This concept is familiar to anyone that has made lemonade from a concentrated powder. Unlike lemonade, however, chemical substances do not usually come in pre-measured packets. In the laboratory, substances are measured in units of moles or grams. Remember, a mole is equal to 6.02 times 10 to the 23rd particles of any substance. Molarity, abbreviated as a capital M, describes the concentration of a solution, as determined by the number of moles of solute in 1 liter of solution. The product of the molarities of hydronium and hydroxide ions in water and aqueous solutions has been determined to be a constant, expressed as Kw, the ion product constant for water. Kw reflects the relative concentrations of hydronium and hydroxide ions as a steady state, even though water molecules are constantly interacting, forming ions and reforming water molecules. The ion product constant, Kw, relates the molar concentration of hydronium ions to the molar concentration of hydroxide ions. In pure water, the only source of these ions is the self-ionization of water, so these two concentrations are equal. Experiments have shown that the molar concentration of each ion at 25 degrees Celsius is 1 × 10 to the -7th moles per liter. To determine the ion product constant for water, multiply the concentration of hydronium ions by the concentration of hydroxide ions. When multiplying numbers represented by scientific notation, multiply the coefficients. In this case, 1 × 1, and then add the exponents. In this case, -7 plus -7, which equals -14. Thus, the ion product constant is 1 × 10 to the -14th. The ion product constant does not have units. Kw is important, as you will see when you learn how to determine pH later in this program. The previous several scenes have described the nature of the hydrogen atom, a brief definition of acids and bases, and the chemistry of water. But how do these concepts interact to form the framework of acid-base chemistry? A water molecule, composed of 2 hydrogen atoms and 1 oxygen atom, can spontaneously dissociate, freeing a positively charged hydrogen ion, which is quickly accepted by a nearby water molecule and forms a hydronium ion and a negatively charged hydroxide ion. Hydronium ions are responsible for the acidic properties of solutions, and hydroxide ions are responsible for the basic properties of solutions. Arrhenius defined an acid as a substance that dissociates in water to produce hydrogen ions, and a base as a substance that dissociates in water to produce hydroxide ions. Although the Arrhenius model is still widely applied today, it has several limitations. The Arrhenius definition restricts acids and bases to aqueous solutions, even though similar reactions can occur between gases or in solvents other than water. Furthermore, the Arrhenius definition of a base excludes compounds such as ammonia, which exhibit the properties of a base but do not contain hydroxide ions. To overcome these limitations, chemists defined acids and bases in broader terms. Most acid-base chemistry concerns the transfer of hydrogen ions. In 1923, Danish chemist Johannes Bronsted and English chemist Thomas Lowry separately proposed a definition of acids and bases based on the transfer of hydrogen ions. The Bronsted-Lowry definition defines an acid as a hydrogen ion donor and a base as a hydrogen ion acceptor. In the reaction on your screen, hydrogen chloride is a Bronsted-Lowry acid, and water acts as a Bronsted-Lowry base. The Bronsted-Lowry model serves to include many acids and bases that were not considered within the more narrow Arrhenius definition. Another model for acids and bases was proposed by Gilbert Lewis in the 1920s. Lewis described acids and bases in terms of electrons. According to the Lewis model, an acid-base reaction takes place when one chemical species shares a pair of electrons with another. The species that accepts the electron pair is an acid. The species that donates the electron pair is a base. Consider the reaction between the gases boron trifluoride and ammonia. Here, boron trifluoride acts as a Lewis acid by accepting an electron pair, and ammonia serves as the Lewis base because it donates an electron pair. The Lewis model is the most general definition of acids and bases because it is based on electron transfer. One valuable aspect of the Lewis model is that it includes many reactions that are not included within the Arrhenius and Bronsted-Lowry models. The Lewis definition is not restricted to aqueous solutions, like the Arrhenius definition, and does not involve proton transfers, as the Bronsted-Lowry definition requires. However, since this program will concentrate on the properties of acids and bases in solution, the Arrhenius and Bronsted-Lowry definitions will be referred to most frequently. Acids may be classified by the number of ionizable hydrogen ions the compound contains. You can think of an ionizable hydrogen as one that is capable of being donated to solution. A compound such as hydrochloric acid, HCl, is called a monoprotic acid because upon dissociation, the compound donates one proton to solution. Likewise, sulfuric acid, H2SO4, or any acid that contains two ionizable protons, is known as a diprotic acid. Phosphoric acid, H3PO4, contains three ionizable protons, and therefore is known as a triprotic acid. When an acid, such as hydrochloric acid, dissociates to contribute hydrogen ions to solution, the concentration of hydronium ions changes. Can you see how a rapid increase in the concentration of hydronium ions results as the protons are accepted by surrounding water molecules? Hydrogen ions are also accepted by hydroxide ions, forming water molecules and lowering the concentration of hydroxide ions. Acids increase the concentration of hydronium ions and decrease the concentration of hydroxide ions in a solution. What about the effect of the chloride ion? The chloride ion has little effect on the acidity of the solution because acid-base solutions are defined entirely by their concentrations of hydronium ions. As you just learned, the acid or base properties of a solution are described in terms of hydronium ion concentration. Since the actual number of ions is measured in moles, and the mole is an incredibly large number, the concentration of hydronium ions is typically written as a negative exponent, representing a fraction of a mole. For example, the fraction 1/1000th of a mole in a liter of solution would be expressed as 1 times 10 to the minus third molar. Remember, the larger the negative exponent, the smaller the actual number. In a very acidic solution such as battery acid, the concentration of hydronium ions may be as high as 1 times 10 to the minus second molar. Compare the concentration of hydronium ions in battery acid to the concentration of hydronium ions in pure water, 1 times 10 to the minus 7th molar. Because 10 to the minus 2 divided by 10 to the minus 7th is 10 to the 5th, the concentration of hydronium ions is 100,000 times higher in battery acid than in pure water. In a very alkaline solution, such as laundry bleach, the concentration of hydronium ions may be as low as 1 times 10 to the minus 12th molar. As you just learned, the acidity of a solution is determined by the molar concentration of hydronium ions. However, many people are unfamiliar with the meaning of exponential numbers or are uncomfortable with their use. Fortunately, Søren Sørensen, a Danish biochemist, came up with another way to describe the concentration of hydronium ions in solution. Sørensen's scale, known as the pH scale, ranges in numerical value from 0 to 14. The abbreviation pH is derived from the German phrase potens Hydrogen. Potens, the German word for power, describes the exponential power of 10 in the hydrogen ion concentration that each unit of the scale represents. All compounds and solutions can be classified as either acidic, basic, or neutral. pH values below 7 indicate a solution is acidic. pH values above 7 indicate a basic solution. Any substance with a pH of exactly 7, such as pure water, is neutral, being neither an acid nor a base. Pure water is neutral, meaning it is neither acidic nor basic, because the concentration of hydronium ions and hydroxide ions are in equal concentrations of 1 times 10 to the negative 7th moles per liter. To understand the logic of the pH scale, it helps to realize that the molarity, as indicated by pH, reflects only the concentration of hydronium ions. The base 10 logarithm, also called the log of a number, represents the power to which 10 must be raised in order for it to equal a given number. For instance, 100 is equal to 10 to the second. So the logarithm of 100 is 2. Logs allow one to represent very large or very small numbers, such as molar concentrations, in a more compact form. pH is defined as the negative log of the molar hydronium ion concentration. The log of a number written in scientific notation is equal to the log of the coefficient added to the power to which 10 is raised. To determine the pH of water, start by noting that the concentration of hydronium ions in pure water is 1 times 10 to the negative 7 moles per liter. The log of the coefficient, which is 1, equals 0, because 1 equals 10 to the 0 power. The log of the coefficient, in this case 0, is added to the log of 10 to the negative 7th, which equals negative 7. Since pH is defined as the negative log of the hydronium ion concentration, the pH value is 7, because a negative times a negative is a positive. Can you see how solutions containing various molar concentrations of hydronium ions are expressed as pH values? By now, you should recognize that a solution with a hydronium ion concentration of 1 times 10 to the minus 3rd molar has a pH of 3. But what if the coefficient is not 1? For example, what would be the pH of a solution with a hydronium ion concentration of 1.4 times 10 to the minus 3rd molar? This presents a slight problem, but one that you can handle. Simply add the log of the coefficient, which is 1.4, to the log of 10 to the negative 3rd. The value of the log of 1.4 is 0.1461. And of course, the log of 10 to the negative 3rd is negative 3. This means the log of the concentration of hydronium ions is negative 2.854. pH is the negative log of the concentration of hydronium ions, so the pH is 2.854. The final answer, 2.85, is rounded to 2 digits beyond the decimal point, because the number of digits reported beyond the decimal point must equal the number of significant digits in the given molar concentration. Now think about the answer, 2.85. A hydrogen ion concentration of 1.0 times 10 to the minus 3rd molar would equal a pH of exactly 3. So a slightly higher concentration of hydrogen ions, 1.4 times 10 to the minus 3rd molar, should decrease the pH slightly, resulting in a more acidic solution, as indicated by the answer 2.85. In a neutral solution, hydronium and hydroxide ions exist in equal concentrations as expressed by the ion constant for water, Kw. However, most solutions are not perfectly neutral. In the simplest of terms, you can think of these two ions as two children on a teeter-totter. When one child goes up, the other must go down, and vice versa. If the concentration of hydronium ions decreases, then the concentration of hydroxide ions increases, and likewise, if the concentration of hydronium ions increases, then the concentration of hydroxide ions must decrease. You have already learned that the product of the concentration of hydroxide ions and the concentration of hydronium ions equals the ion product constant, 1 times 10 to the minus 14th. Therefore, dividing the ion product constant by a known concentration of hydroxide ions gives you the concentration of hydronium ions. For example, if the concentration of hydroxide ions in a solution is 3.5 times 10 to the minus second molar, what is the concentration of hydronium ions? Dividing the ion product constant of 1 times 10 to the minus 14th by the concentration of hydroxide ions, 3.5 times 10 to the minus second molar, gives you a hydronium ion concentration of 2.86 times 10 to the minus 13th molar. Do you remember how to convert molar concentration to pH? Add the log of 2.86, which is 0.4563, to the log of 10 to the minus 13th, which is negative 13. This gives you a log of minus 12.5437, and multiplying by negative 1 gives a pH of 12.5437. Now, round the answer to 2 places past the decimal point, which gives a pH of 12.54. In summary, the acid-base properties of a solution are determined by the concentration of hydronium ions. These ions occur naturally in solution due to the self-ionization of water molecules. The product of the concentrations of hydronium and hydroxide ions in aqueous solution is known as the ion product constant of water and is represented by the symbol Kw. Since numbers of ions are reported in units of moles, the actual number of ions is a fraction of a mole written in exponential notation. The pH concept converts these small values to positive numbers on the 14-unit pH scale. Neutral solutions with equal numbers of hydroxide and hydronium ions have a pH of exactly 7.0. A solution in which hydronium ions outnumber hydroxide ions is acidic and will have a pH below 7.0. A solution in which hydroxide ions outnumber hydronium ions is basic, or alkaline, and will have a pH above 7.0. Some compounds function as either an acid or a base, depending on the reaction. These substances are defined as amphoteric. The term amphoteric is taken from the Greek language and means partly one and partly the other. In acid-base chemistry, amphoteric compounds can act as both proton donors or proton acceptors. Though many substances may have amphoteric properties, the best-known amphoteric compound is water. In this reaction, for example, water, acting as an acid, donates a hydrogen ion to ammonia, forming ammonium ion. However, when water reacts with hydrochloric acid, it acts as a base, accepting a hydrogen ion, forming the hydronium ion. The equation on your screen shows the reversible reaction of acetic acid and water. As the reaction proceeds from left to right, acetic acid ionizes and transfers a hydrogen ion to water, creating the products, a hydronium ion and an acetate ion. Because acetic acid donates a proton, by the Bronsted-Lowry definition, it acts as an acid. By accepting a proton, water acts as a Bronsted-Lowry base. In the reverse direction, right to left, the hydronium ion donates a proton to the acetate ion. In this case, the hydronium ion is acting as an acid by donating a proton, and the acetate ion is acting as a base by accepting a proton. Notice that water acts as a base on the left side of the equation and forms the hydronium ion, which acts as an acid on the right side of the equation. The hydronium ion is therefore referred to as the conjugate acid of water. Acetic acid acts as an acid on the left side of the reaction and forms an ion that acts as a base on the right side of the equation. The acetate ion is known as the conjugate base of acetic acid. The conjugate acid of a substance is formed when the substance gains a proton. In the same vein, a conjugate base of a substance is formed when the substance has donated a proton. A substance and its conjugate are known as a conjugate acid-base pair. Now, take a look at the reversible reaction of ammonia in an aqueous solution. As the reaction proceeds from left to right, aqueous ammonia acts as a base, accepting a proton from water. Since water is donating a proton, it is acting as an acid. In the reverse reaction, the ammonium ion is the conjugate acid of ammonia and acts as an acid because it donates a proton to the hydroxide ion. The hydroxide ion is the conjugate base of water because it accepts the proton. In this reaction, ammonia and the ammonium ion are a conjugate acid-base pair. A line is often used to connect a conjugate acid-base pair to one another. You may also have noticed that there is another conjugate acid-base pair. Do you see that the water molecule is an acid in this reaction, and that the hydroxide ion is its conjugate base? As you can see from the chart provided, there is an inverse relationship between the strengths of the members of a conjugate acid-base pair. This means that the stronger an acid, the weaker its conjugate base, and the stronger a base, the weaker its conjugate acid. Compare formic acid, which is responsible for the painful bite of a red ant, to a weaker acid, acetic acid. The conjugate base of formic acid, the formate ion, is a weaker base than the conjugate base of acetic acid, the acetate ion. In simple terms, the more eager an acid is to give up its proton, that is, the stronger the acid is, the less eager its conjugate base will be to pick up a proton. In similar fashion, the more likely a base is to accept a proton, the less likely its conjugate acid will be to give up that proton. In chemistry, acids are broken up into two broad categories: strong acids and weak acids. It is important to note that these terms are not synonymous with low pH and high pH. Depending on concentration, a solution of a strong acid, such as hydrochloric acid, can have a pH close to neutral, and a solution of a weak acid, such as acetic acid, can have a low pH, meaning it is far from neutral. A strong acid is one that dissociates completely in water. For example, in an aqueous solution of hydrogen chloride, there are essentially no hydrogen chloride molecules in solution because they all dissociate to produce hydrogen ions and chloride ions. This means 1 mole of hydrogen chloride in solution produces 1 mole of hydronium ions. In contrast, in an aqueous solution of hydrofluoric acid, most of the acid does not dissociate. This means 1 mole of hydrofluoric acid, or any other weak acid, will produce less than 1 mole of hydronium ions. A measure of the strength of weak acids, the acid dissociation constant, will be discussed in the next few scenes. The acid dissociation constant, Ka, quantifies the extent of dissociation among weak acids. This allows comparison of the relative strengths of weak acids and calculations of their pHs to be made. Ka is derived from the equilibrium equation of a weak acid that dissociates in aqueous solution. If the acid is represented as Ha, the balanced chemical equation is Ha plus H2O yields H3O plus A minus. At equilibrium, this can be represented as Keq equals a concentration of H3O plus times a concentration of A minus divided by a concentration of Ha times a concentration of H2O, where Keq is known as the equilibrium constant. As with the ion product constant, the concentration of water in the dilute solutions made by weak acids is essentially a constant. Multiplying both sides of the equation by the concentration of water removes the term from the denominator on the right side of the equation and separates the variables from the constants. The product of the two constants on the left side, Keq, and the concentration of water gives a new constant, Ka, called the acid dissociation constant. Since a strong acid completely dissociates in water, the denominator of the acid dissociation constant expression would be 0, and the value of the expression would be undefined. This is why Ka is typically used only for weak acids. Like the ion product constant, the acid dissociation constant has no units. As you just learned, the acid dissociation constant, Ka, is used to describe the behavior of acids in an aqueous solution. Keep in mind, an aqueous solution is a solution in which the solvent is water. The acid dissociation constant, Ka, represents the degree to which an acid dissociates or splits apart in water. Observing the Ka expression for acetic acid will help you visualize how the mathematical expression relates to actual acids and the ions they form in solution. What does the acid dissociation constant Ka really mean? The larger the given Ka value, the more the acid dissociates in water to form hydronium ions, and therefore the stronger the acid. Each weak acid has a characteristic Ka value. Weak acids have a dissociation constant, Ka, of much less than 1, indicating that only a fraction of the acid molecules dissociate in water. By looking at the table provided for you on your screen, can you determine that acetic acid is a weaker acid than chlorous acid? A base can contribute hydroxide ions to an aqueous solution in 2 ways. Bases may ionize, resulting in a direct increase in hydroxide ion concentration, Or they may attract hydrogen ions from water molecules, resulting in an indirect increase in hydroxide ions. Remember that when a base, symbolized as B, accepts a proton, it becomes the conjugate acid of that base, symbolized as Hb+. Derived in a fashion similar to the acid dissociation constant, the base dissociation constant, expressed as Kb, represents the contribution of hydroxide ion to solution by a weak base. The larger the Kb value, the stronger the base, and the greater the contribution of hydroxide ions to solution. Observe how the expression illustrates the contribution of hydroxide ions by aqueous ammonia. Strong bases dissociate in water to release hydroxide ions, or attract hydrogen ions from water to form hydroxide ions. Compounds such as sodium hydroxide that completely ionize in solution are strong bases. Like strong acids, strong bases completely ionize in water, so Kb values are not typically used for strong bases. Weak bases only partially dissociate in water. The smaller the Kb value, the smaller the extent of dissociation, and therefore the weaker the base. There are several common weak bases, such as ammonia, NH3. By looking at the table provided for you on your screen, can you determine that methylamine is a stronger base than ammonia? You have learned that the pH of a solution is based on the concentration of hydronium ions. You also know that bases increase the concentration of hydroxide ions by directly donating them, or indirectly by accepting hydrogen ions. Neutralization describes the process of bringing a solution closer to a neutral pH. A base can neutralize an acidic solution by attracting protons. In the same vein, acids neutralize basic solutions by donating protons. Hydroxide ions have a strong affinity for hydrogen ions and will attract them from nearby hydronium ions, resulting in the formation of two water molecules. Some bases, such as ammonia, do not release hydroxide ions, but instead steal protons from hydronium ions, forming water and ammonium ion. Regardless of the mechanism, bases neutralize acids, and acids neutralize basic solutions, bringing a solution's pH closer to neutral. Neutralization reactions often result in the formation of water molecules and in ionic compounds called salts, which you will learn about in the next section of this program. Now that you are familiar with some aspects of acid-base chemistry, we can turn our attention to a related class of compounds, salts. Salts are ionic compounds composed of any positive ion other than hydrogen and any negative ion other than hydroxide or oxide. Acids and bases can react to form salts. Like couples in a chemical dance, the ions from acids and bases exchange partners, thus forming a salt. Although salts are formed from acids and bases, they exhibit almost none of the properties of their parent compounds. Whereas acids and bases react with other compounds, most salts are relatively non-reactive. Acids and bases usually exist as a liquid or gas, while salts form solids. Salts form solid structures known as crystals. The properties of salts result from the arrangement of ions within these crystals. Attraction between oppositely charged ions and repulsion between ions of the same charge are strong. Consequently, Ions with opposite charges in a salt crystal align in an alternating pattern. The resulting crystal lattice gives salts their hard yet brittle properties. The bonds between the positive and negative ions are very strong. Therefore, ionic compounds such as salts are difficult to crush and are not very pliable. However, when struck sharply, they easily break or shatter because ions in the crystal lattice shift, causing like charges to align and repel one another. The repulsion between ions with the same charge becomes so intense that the crystal shatters. At a temperature specific to each salt, the energy from heat is great enough to overcome the strong attractions between the positive and negative ions within a crystal. This temperature is called the melting point. Salts exhibit high melting points because the bonds between positive and negative ions are very strong. At room temperature, ions within a crystal are tightly packed next to one another. Although they are constantly vibrating in place, they cannot move about within the lattice structure because the bonds are too strong. When heated, the ions gain energy and begin to move within the lattice, bouncing off one another. One property that the crystal lattice does not confer upon salts is electrical conductivity. Normally, electricity cannot flow through the fixed ions in the lattice. Ionic compounds only conduct electricity when dissolved in solution or when a solid melts. When an electrolyte, such as sodium chloride, melts or dissolves, the positive and negative ions separate and are free to move about. In the liquid state and in solutions, ions are responsible for the transport of electrical charge through the solution. Although the best-known salt by far is sodium chloride, there are many different salt compounds, and some of them are commonly used by humans. Ammonium sulfate and ammonium nitrate are included in many commercial fertilizers. These salts ionize in the presence of water to add nitrogen and sulfur to soils depleted of these elements. Calcium sulfate, known commonly as plaster, is used to form casts. Potassium nitrate is used in the manufacture of explosives, including these fireworks. As you learned earlier, pure water has a pH of exactly 7. Normal rainwater has a pH of about 5.6, which is slightly acidic. The acidic pH of rain occurs because some of the carbon dioxide in the atmosphere reacts with water as rain falls to Earth, forming carbonic acid, H2CO3. You are probably familiar with the term acid rain. Acid rain has a pH below that of normal rainwater. Acid rain results primarily from air pollution produced by sources such as industrial emissions, car exhausts, and volcanic eruptions. Most air pollution is a combination of sulfur dioxide and nitrogen oxides. These gases react with water vapor to form weak solutions of sulfuric and nitric acid, which fall to Earth as acid rain. Acid rain can have a variety of detrimental effects on ecosystems. When acid rain decreases the pH of lakes and rivers, it can affect the amphibians, fish, and other animals that live there. When it falls on land, it disrupts plant life and can even disturb entire forests. Acid rain also causes damage to man-made structures, such as sculptures, and even historical buildings and bridges, which may be rendered unsafe. In this program, you learn that acids and bases can be potentially dangerous compounds, and that safety should always be a consideration when handling these substances. Several definitions serve to describe the chemical behavior of acids and bases. This presentation has focused on the Arrhenius, Bronsted-Lowry, and Lewis models. You have learned that the concept of pH serves to convert molar concentrations of hydronium ions into values arranged on a scale from 0 to 14. The concept of strong and weak acids and bases was also discussed, based on the degree of ionization that takes place when an acid or base dissolves in water. Salts result from reactions between acids and bases. Salts, such as sodium chloride, display very different properties from either acids or bases, and are usually found as crystalline solids. And finally, you learned about some of the impacts that acid rain has on the environment.